Hey everybody, so we're moving on to our next step in the Lewis structure covalent bonding chapter of our lives. Molecular geometry. We know that compounds form certain structures. Well, these structures have names. So what I'm going to have you do is I'm going to have you go to our classroom and look at this worksheet here. You can print this off, you can look on it, look at it at another tab, but you can't, and you can use it on any quizzes or worksheets. You can't use it on a test though. But the good thing is that you don't have to memorize these bottom two rows. All you got to do is worry about these first three rows, and that's only 6 molecular geometry structures that you have to memorize. So go ahead, download this, because we're going to be learning how to decipher this guy here in just a moment. We're also going to be talking about polarity today. Okay, you need to be able to know if molecules are polar or nonpolar. This helps us decide tons of things. It helps us decide what dissolves, what doesn't dissolve, if things will eat our skin or not. Okay, this is a very important thing. So our goal today is to be able to list molecular geometry and bond angles of certain structures, and to list if they're polar or nonpolar. So let's get started. So I'm going to go ahead and I'm going to tell you what domains are. You're going to hear me say domains a lot. And that's just grouping of electrons around a central atom. Okay, a domain can be a single bond, a domain can be a double bond, it can be a triple bond, or it could be a lone pair. Each of those count as one domain. Some of you will see a double bond and think, hey, that's 2 domains. Nope, it's just one domain. So if we were to look at something like CH4, and I asked you how many domains are around that carbon atom, you would say 1, 2, 3, 4 domains. If I were to look at something like CO2, and I ask you how many domains are around that carbon atom, 1, 2 domains. Alright? And then let's do one more example like that, where we got something like H2O. How many domains are around that oxygen atom? 1, 2, 3, 4. And that will come in handy. Okay, that will come in real handy later. So be aware when I say domain what I'm talking about. I'm just talking about groups of electrons around that central atom. So let's look at our worksheet and let's look at this first molecular geometry there, which is linear. A great example of this is beryllium dichloride and what I just drew a little bit ago, CO2. Remember, those electrons are going to try to get away from each other as much as possible. This is called the separator, okay? Which just means valence shell electron pair repulsion. That just means that electrons, since they're negatively charged, are going to get away from each other as far as possible. And when they do that, they form these nice little shapes, like beryllium dichloride forms this shape, and carbon dioxide forms this shape, okay? And what we end up calling this shape is linear, okay? Linear. And the next thing, that's the molecular geometry, and the next thing they'll ask you is, what is the bond angle? Well, the bond angle is just the angle between the 2 domains here, which happens to be 180 degrees. It's the same thing with this carbon dioxide. It might be slightly smaller, but for the most part, it is 180 degrees as well. So when you see something with just 2 atoms around it, or 2 domains around it, you're thinking linear, 180 degrees, which is our first one there. Now let's talk about polarity for a second. Polarity is the distribution of electrons, okay? If something is polar, it's got an uneven distribution of electrons. If something is nonpolar, it doesn't. So what I want you, this has to deal with our dipole moments, by the way, but what I want you to think of is this central atom, and these chlorines are pulling on it with a certain amount of strength, with a certain amount of electronegativity. But imagine that these chlorines have a rope and they're pulling on this beryllium. And the chlorine strength, or the element strength, depends on what kind of element it is. And it's based on their electronegativities. So chlorines since they are the same element, they have the same amount of strength, the same amount of electron pull. So if these guys both have the same amount of strength, both these Cls, and they pull on that beryllium, is beryllium going to shift one way or the other? Is it going to be pulled more to the right, those electrons, or are they going to be pulled more to the left? And the answer should be no, right? If chlorines both have the same strength, that beryllium is just going to stay right there. It's not going to be pulled in any certain direction. So there is no pull. So that means that this guy is non-polar. That means he is non-polar. And a little sidetrack on this guy, okay? Or on polarity. Likes dissolve likes. So things that are polar dissolve other polar things. That's why salt dissolves in water. Salt is polar, water is polar. That is why your skin doesn't get eaten up by water. Your skin has oils on it that are very non-polar, so when water gets on it, it doesn't eat away that stuff. It just kind of slides right off your skin without dissolving anything. It's the reason why if you get butter on your hands, okay, butter is very non-polar. So if you try to get water on it, it's not going to wash it away. Okay, that's the good thing about soap. Soap is this long, non-polar chain of molecules with a polar end on it. So soap is nice because it's got a polar end on it that can dissolve away, or it's got a non-polar end and a polar end, so it can dissolve away some of that butter or oil or grease or whatever's on your hands, and then that water can go ahead and wash the rest of it away. So that's what soap does. It breaks down any non-polar or polar stuff on your hands. That's why sometimes if you use too much Dawn dish soap, remember it is slightly polar, so it can burn you a little bit. It can eat into your skin. That's why acids are so dangerous. They are so polar that even though you got non-polar oil on your skin, it can still eat away at it. Okay, so remember, likes dissolve likes, polar dissolve polar things, non-polar things dissolve non-polar things. That's why you get different kind of oils and liquids when you put them together. They separate out. It's because they're not going to mix, because they're both different polarities. So if I'm looking at this guy right here, these oxygens, if they both pull on that carbon, is that carbon going to shift one way or the other? The answer is no. This guy is non-polar as well. And just a quick thought experiment here. If I ended up making up one of these atoms H, okay, now, is this top molecule going to be polar or non-polar? Well, remember that these guys are now pulling with different strengths. They're not the same element anymore. Actually, chlorine is a lot more electronegative, so your dipole moment is going to be shifting that way. So when both these atoms pull with the same strength, guess which way those electrons are going to shift more. It's going to shift more to the left. So this guy now is actually polar. Okay, be aware of that. Be aware if there's a difference in poles, if there's different atoms around the outside, there's going to be a different shift. And if there is a pole, it's polar. If there's no pole, they cancel each other out like this guy. It'll be not polar. Alright, let's go ahead and look at our next compound. Let's go ahead and look at BH3. Okay, BH3, it has 3 domains around it. If it's got 3 domains around it, 1, 2, 3, it's always going to be 120 degrees. And since it's got 3 atoms around it and no lone pairs, its name is trigonal because it's got 3 atoms surrounding it. And it is called planar. Why is it called trigonal planar? Well, if we look at BH3, right, it's got trigonal because of those 3 atoms, like I said, but it's planar because if you turn it sideways, it's on just one plane, right? There's nothing sticking up in any other direction. It's trigonal planar because it's on one plane, and it's got that nice bond angle of 120 degrees. Okay, let's look at this thing and see if it's polar or non-polar. I'm looking at this remember, all those hydrogens, since they're the same, they're going to be pulling with the same strength. So if they're pulling with the same strength, the same electronegativity, is that boron going to get pulled any certain way? Imagine if you and your buddies pulled on another buddy with the same strength by his arms and leg, and would he move in any direction? No, he would stay right there in the middle. Same with this boron. He's not going anywhere. He is non-polar. The other type of molecule that you'll see with 3 domains is something like, we'll go with that boron again, but instead of another hydrogen, it's going to have a lone pair on it instead. It's got 3 domains, 1, 2, 3, so it's still going to have a 120-degree bond angle. Okay, if it's got 3 domains, it's going to be a 120-degree bond angle. But in this case, it's no longer trigonal planar, it is now bent. As you can imagine, because it has a bent shape. Alright, so that is bent. Now, polar or nonpolar. Here's a trick for you. If there is ever a lone pair on the central atom, it's polar. Okay, this guy is polar. The reason being, if these guys were directly across from one another, okay, like so, they would cancel each other out. But what happens when we add that lone pair is it shifts those hydrogens downward, and then when they pull on this atom, they are pulling on it unevenly. There is a uneven dipole moment, and it pulls it downward. Those electrons are misdistributed, so it makes it polar. And that's with any compound that has a lone pair on the central atom, as far as honors chemistry is concerned. Okay? So whenever you see a lone pair on the central atom, you're always thinking polar, because that misdistribution of the dipole moment. Now let's talk about all our 4-domain molecular geometries. We got our 4-domain ones like CH4, NH3, and H2O. Okay? All these guys have 4 domains, right? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So they're always going to have a bond angle of 109.5, which I always say is our favorite radio station, 109.5. So you see anything with 4 domains, always a bond angle of 109.5. And you might be thinking, hey, that looks like 90 degrees there. But remember, this is on a 2D plane, and we don't live in a 2D plane. We live in a 3D world, okay? So when those guys are going to get as far away from each other in 3D, they're going to form a molecule that looks like this, which happens to form a bond angle of 109.5. Alright? So this first molecular geometry, 1, 2, 3, 4 atoms around it. So this one is called tetrahedral. When you see tetra, right, that's 4. That's why they call the game Tetris, because every block is made out of 4 squares. Fun fact for you. Right? That's why they call it Tetris. That's what tetra means. Tetrahedral, 4 atoms. This guy, our next one, NH3. It's got 3 atoms around it, so once again it's trigonal. But unlike our trigonal planar, it is now trigonal pyramidal. You call it trigonal pyramid or trigonal pyramidal. And the reason that is because that lone pair shifts those atoms downward, and it kind of forms a little pyramid shape. Okay, so that's why they call it trigonal pyramidal. Trigonal because there's 3 atoms, pyramidal because that lone pair shifts things downward. And now we're looking at our last one, which is H2O. Okay, those 2 atoms get pushed down from those 2 lone pairs, so it gives off this shape right here, which ends up being called bent as well. So that is bent because those 2 lone pairs shift those hydrogens down into a nice bent shape. But as you can see, those 4 domains are still 109.5 degrees apart. So we're looking at this. Let's talk about polarity. This guy, polar or nonpolar? Nonpolar. Reason being, I'm just going to put NP right here. Hydrogens all pulling with the same strength. That carbon's not getting pulled anywhere. Those electrons, those electronegativities are evenly distributed. Trigonal pyramid. What about that guy? That guy is going to be polar because lone pair on the central atom, right? That causes those atoms to shift downward, creates an uneven pull of electrons, creates that dipole moment, which gives you a polar molecule. Same can be said for our water, right? Those lone pairs on the central atom shift those atoms downward, create an uneven pull of electrons, making it polar. Those are all of our molecular geometries and bond angles. Let's go ahead and do a few examples and then we'll be done. So we have our 3 examples here. We got CH3Cl, N2, and SO3. If we were to draw the Lewis structures for all of these after following our rules, we would get something like these guys. Let's go ahead and give the molecular geometry, bond angle, and polarity for each of these. If you look at CH3Cl, we look at that and we see, let's figure out how many domains there are around that central atom. 1, 2, 3, 4. So remember, if there's 4 domains, it's our favorite radio station, 109.5 degrees. When we see this, we see that that central atom is surrounded by 4 atoms. If it's surrounded by 4 atoms, it's called our tetrahedron. Tetrahedron. And then we look at polarity, right? If they were all hydrogens, it'd be nonpolar because they'd all pull with the same strength. But unfortunately, we got this chlorine over here that has a different strength, and it's going to pull those electrons a lot more, and it's going to make this guy polar. N2, right? N2, you could focus on either of these nitrogens and figure out how many domains are around it. Well, if I look at this nitrogen, it's got 1, 2 domains. If I look at this nitrogen, it's got 1, 2 domains. All right, again, those nitrogens are going to try to spread those electrons as far away from each other as possible. And in this situation, when there's only 2 atoms, it's always going to be 180 degrees. If something has a bond angle of 180 degrees, it's going to have a molecular geometry that is a straight line or linear. Let's look at polarity, right? Those are the same atoms. Are those going to pull electrons more than one way or the other? And the answer is no. They're going to pull on those electrons with the same strength because they got the same electronegativity. So there is no pull on electrons, or it is non-polar. I look at SO3. I look at how many domains are around that sulfur atom. I got 1, 2, 3 domains. If I got 3 domains, that's 120 degrees. It's surrounded by 3 atoms. There's no lone pair on that guy. So if it's only surrounded by 3 atoms only, it's going to be trigonal for each atom, and it's going to be planar, because those guys can get as far away from each other as possible and form that nice plane geometry. Right? If I add a lone pair in there, then it ends up turning into this trigonal pyramid, but that's not what it is. And the next thing is polarity. Some of you might be thinking, hey, that double bond, doesn't that cause a pull of an uneven pull? No. We don't care about the bonds. We only care about the surrounding atoms around that central atom. So all those atoms are the same, right? They're all oxygens. There's no lone pair on that central atom. All those oxygens pull with the same electronegativity. So it's going to be non-polar. There's no uneven distribution even with that double bond in there. Alright, so that is molecular geometry. Make sure you're familiarizing yourself with that, being able to list bond angle, molecular geometry, and polarity, and also have yourselves a great day.